I'm really excited to tell you today about my work last fall with Mike and Julianne on the high-resolution StarForge simulations and how we are able to compare those to observable properties. So I wanted to start my talk today by just showing one of these amazing simulations. I've been a long-time admirer of the StarForge work, may or may not have shed a tear the first time I saw these. But the StarForge simulation suite is really pushing the envelope in terms of what's capable of, in terms of the mass resolution and the physical scales that are being probed here, while also fully incorporating stellar feedback into the star formation prescription. So what we're seeing here is a cloud that is collapsed and forms filaments, and then along those filaments, stars are forming. And importantly, what we're seeing right here is the feedback from the most massive stars, which is going to be extremely prevalent in our story today. So when I first came to the CCA, I was an observer, knowing nothing about simulations, looking a lot at these type of objects. This is an object in M33, a local group galaxy. This is a star cluster. This is an image taken combined with HST and JWST, where we're able to individually resolve the stars in this simulation. And so one of the things that's most exciting is taking these observables in the local group galaxies and then being able to directly compare that to these high-resolution simulations. Now, looking at the differences between what I have shown on the left and on the right is the thing that we have identified in local group galaxies is a little bit more spherical in nature in our assumptions, right? Just in our assumptions. But actually, when we take a better look at the simulations, as we kind of rotate around our viewing angle and our perspective, we actually see a lot more filamentary structure, and that it's maybe not quite as spherical as we thought. And so as we're going around, we're also looking through a lot more different column densities of gas and dust. And so just taking the stars in the simulation and kind of rotating around this viewing sphere, we see incredibly bright stars that entirely disappear when they pass behind different column densities of gas and dust. And so this regime, where you have both of these properties, you have stars that are in the process of forming, and you have gas and dust in the system, is called an embedded cluster. And in particular, the timescales for how long this stage of the star formation period lasts is one of the main projects that I was working on here at the CCA. So in order to do this, taking out of video mode for a second and going to snapshot mode, we have shown here in the color maps are the gas density of the simulations across simulation time, shown at 3 different viewing angles. And in particular, what we see is specifically at this late time, once the gases begin to be expelled from the system, depending on how we are viewing the system, going back to our movie, the observability of the stars can be changed. So specifically linking back to observable properties of the star cluster, we're trying to come up with a way of defining the stellar extinction for the stars as a function of time. And so the way that we do this is we went 60 different viewing angles around a sphere and determined the optical extinction at each viewing angle. So shown on the x-axis is the median extinction per star, and then on the y-axis is the ratio between each individual viewing angle compared to the median. So then what we see is this general trend where for stars that are highly extincted, like 10 to the 3 AV, the typical extinction level is going to then scatter towards lower values, meaning that there are a few sight lines that are free of gas and dust. And the inverse is then true for stars that are nearly entirely exposed. There may still be 1 or 2 sight lines that have gas and dust. So taking this definition of extinction, this kind of twiddle AV that we're going to come back to a lot today, going back to our simulation snapshots, now that we have defined our observable tracer, this extinction, we're able to track the overall association extinction as a function of time. And so what is shown as red is the fraction of stars which have an AV greater than 1, and then shown in brown are the stars that have a median overall extinction greater than 10. So these are the stars that we would definitely not detect in the optical. Overall, we see this very rapid transition between the embedded stage and the exposed stage, taking about 2 million years from when the gas is first expelled from the system. Importantly, this 2 million year period tracks with the gas expulsion time, which has been measured in the star formation suite, as well as the gas expulsion time that is pretty consistent in the literature. Now, looking at the overall association is amazing, and we can get this really cool characterization of the overall association as a whole. But a lot more can be learned from going to the individual stars in the simulation as well. So that is what's shown here on this plot. We have the points, which are the individual stars, which are colored and sized by their mass. On the x-axis, we have when in the simulation a gas particle turned into a star particle and began to accrete. And then on the y-axis up here, we have the simulation time where that star particle reached its maximum mass. So then simply integrating along the x-axis, we're able to get the total accretion time for that star, which is what's shown down here in this bottom panel, where we have the accretion time for two different mass bins of stars, where low mass stars, stars that are smaller than 1 solar mass, are pretty constant across simulation time in terms of their accretion time. However, stars that are more massive than a solar mass actually depend heavily on when in the simulation they formed in terms of how long they accrete. And this is because the stars are able to accrete their local gas reservoir of gas. And so at the start of the simulation, gas is very prevalent. And as the more stars are forming, more stars are accreting gas. It's becoming less apparent. As feedback is then clearing out the regime of gas, it's becoming even less apparent. And then we have this kind of weird secondary bump here in the accretion time for the massive stars. And this is best explained by taking a better look at the simulation just from this 6 million year time forward. So we still have lots of gas that are present, and we have the stars that have formed up to this point. And then if we play, we can begin to see this crazy gas expulsion from the system. And now we're getting to about 9 million years, and we're still having stars form. So importantly, over the entire simulation time, we see stars being formed. However, the location of this star formation is still happening within the pockets of dense gas within the simulation. So taking a closer look at this snapshot here, we see star formation still occurring, except it's only occurring in places with dense gas. Therefore, the local reservoir of gas that is available for accretion allows for the accretion time for these massive stars to then increase again. So taking a closer look at the overall extinction level for these individual stars, we can track each individual star's extinction as a function of its stellar age. So on the x-axis is a star's age, with 0 being defined to be the point when that star reaches its maximum mass. And on the y-axis, we see the median extinction for that star. Now we see these very distinct tracks in the star age versus extinction curve, where right around the time when a star reaches its maximum mass, it drops from heavily embedded to not quite so embedded. And this is pretty consistent regardless of when in the simulation a star forms. It can form early or late. We see this general trend, which makes sense intuitively, right? So in order for accretion to stop, Mike was telling me about this yesterday, the radiation from the star, the radiation pressure from the feedback, has to overcome the accretion of this thing. So that's how accretion stops in general. So the same mechanism is the mechanism which clears out the gas from the system. So therefore, it makes a lot of sense that when the accretion stops, we begin to see this gas expulsion. This is particularly true for the large points in this GIF here, the high mass stars. However, we see the low mass red points, so these are stars that are smaller than about 0.5 solar mass. We see them being extended a lot further than the high mass stars. So this is indicative of the fact that these low mass stars don't have the energetic feedback required to actually clear out their local regions and then stay embedded longer until the gas and dust is cleared out by a more massive stars. So directly quantifying the level of extinction in the simulation compared to the number of high mass stars and the number of stars which have formed in general is particularly important. So coming back to this extinction curve, which I've showed before, which is the red point, which is the fraction of stars that have an AV greater than 1. We also show the fraction of stars which have formed and the fraction of stars that are higher than 8 solar masses that have formed at each simulation snapshot. And so what I've marked here, the kind of this transition point where we begin to see this like rapid decline, as well as the 50% mark shown here. And so this has been for the simulation that I have been talking about all day today. However, we actually went to a secondary simulation, one that is a lot more massive, to see if this general trend holds true. So shown here in red is everything that I have been talking about up to this point, the same red extinction curve. And then shown in red is the fraction of high mass stars that exist at each snap point. Importantly, we see this downturn here at the very end in both simulations. So this is indicative of supernova explosion, right? So if you have a star that's more massive than 8 solar masses and it explodes, it's no longer there. We don't count it anymore, so we see this downturn. Importantly, at this late time stages of the simulations, we've already seen the gas being efficiently cleared out from the simulation, suggesting that pre-supernova feedback is efficient and it's not required that we have supernova to entirely clear out the region for gas. Now, importantly, both of these simulations kind of experience the same general trend in terms of the extinction, as well as the number of high mass stars that have formed at each simulation snapshot. If we scale this by the free fall time, we see this the overall trend hold very true. And it's not perfect, but it looks very consistent when we just scale the two clouds by the free fall time. So this is evidence that the embedded timescale scales with the overall free fall time of the cloud. Now coming back to just for a moment, I talked a lot about the observability of these star clusters. One of the ways that people have historically viewed embedded clusters is through longer wavelengths or 24 micron emission. So when a high mass star has ionizing photons, it will then be absorbed by the gas and dust, the dust, which is then emitted at longer wavelengths, specifically at 24 microns. So we made some mock observations of the simulation suite at 24 microns. And I get kind of giddy when I see this substructure and the gas here, specifically at this like 7.3 million year time step. Importantly, if we track the overall luminosity of the 24 micron emission as a function of time, we see it peak before the main gas expulsion has taken place, while the high mass stars are still embedded. This intuitively makes sense because of the mechanism which this 24 micron emission is taking place. You need both this gas or the dust and the stars to be highly coupled together. So once the gas and dust are expelled from the system, they're no longer coupled, and this mechanism is not as efficient. Coming back to this first image that I showed, directly comparing some of the things that we have seen in external galaxies to the StarForge simulation suite, there's one thing that becomes pretty apparent, and that is the fact that at 10 million years in the StarForge suite, the system looks like this. There's no long-lived remnant of the star formation past about 10 million years. This is something that Mike has said has kept him up at night. And so moving forward, we have been putting a lot of work into trying to characterize what makes a gravitationally bound stellar cluster and something that is a little bit more long-lived. So we took the high mass simulation that I was referring to a little bit earlier, and then once the simulation ended, we just took the stars and N-body evolved them for 35 million years. And once we did that, we found something that kind of looked like a gravitationally bound cluster, which is extremely exciting. We have named it my special little guy because it is so exciting. And so we're doing a little preliminary work on the gas that goes into forming something that will remain gravitationally bound, and then all the gas that ends up in the stars that are not. I'm going to play this movie side by side, and we can begin to kind of see the different substructures between the gas that goes into something that forms a gravitationally bound cluster and the things that will disperse away. interestingly, especially at this time step, it looks like there's not a lot of physical separation between these two quantities. So over there we have our star cluster that begins to stay gravitationally bound and go away, and then we have our field stars over here. I want to go back for just a moment to this kind of critical moment in this simulation where the physical space of the things that are bound and unbound are tightly coupled. They're both happening towards the very center of the gravitational potential, and yet we see this big kind of southern movement from the thing that stays bound compared to the things that don't. And so this is going to be one of the big future works that is going to come out of in the next couple months, hopefully, trying to really characterize what is going into these stars that makes them stay gravitationally bound for a long period of time. So with that, I will leave up my conclusions, showing that the embedded timescale scales with the cloud freefall time. The transition between embedded and non-embedded is driven by individual massive stars, and it happens relatively quickly. We see stars forming across the entire simulation spanning 10 million years, which form in subclumps. And the IR emission is it's only bright and dominant for a short period of time, even though it is a very dominant mode of observing star formation. And then hopefully trying to characterize this gravitationally bound star cluster in the future. Thanks.
Thank you, Tobin. You are too kind to Starforge. It makes me blush. All right, any questions? Adrian?
Very cool, Tobin. Very excited about the second half, too. I'm very curious about why that bound clump seems to start. It seems to be fairly local. I'm assuming you're in some rest frame, constant rest frame, and then it just starts going towards the bottom of the box.
Mm-hmm.
What causes it to start accelerating?
Mm-hmm.
Good. Okay.
Yeah. Ask me when I come back next year.
Cool. All right. That's sweet.
Yeah, I totally agree.
Look,
I
it's
have no idea.
happy right now. Just in your top right.
I think it's the collapse of the filament.
Okay.
So
But look at that. Look at it now.
no, but
Where's it running away?
But if you, to me, some of the difference between the left and the right is if you're already a star when you're moving in, you can't shock or slow down, and so you just kind of pass through. Whereas the special little guy is
But it's going at kilometer. That's 10 parsecs, 15 megayears. So that's like a kilometer a second. Yeah. Okay. That's cool. Yeah.
It pancakes and filaments, and then it does that. And when it's doing that, it's kind of asymmetric to one side.
Still not convinced the numbers. But,
Amiel?
Two-part question. First part, so in the simulation that you showed, the main simulation, what was the overall star formation efficiency in the end?
Yeah, so I'm going to use round numbers. It's about 10% star formation efficiency.
10%. My question is whether you can relate, in general, whether you've thought about relating the behavior at early times that you can determine by the extinction and what the efficiency is going to be at the end. A way of connecting those two.
Interesting. So you're saying taking the overall efficiency.
Let me just say, I would say, my intuition would say if the AV is higher at early times, you're going to wind up with a higher efficiency, but I'm wondering whether that's true or not.
I am not entirely sure that that's true. I think the efficiency is more sent by the density, which, while you need a high density to have a high extinction, I don't necessarily think the inverse is true. Yeah.
Tobin?
Cool. So in the end, on your conclusion slide, you talked about the IR emission being only for a short time.
Yeah.
Is there a way to use that, or the IR luminosity of a cluster to age it based on if you have a sense of when the massive stars turn on and start irradiating the gas and dust, and then when the gas and dust is dispersed?
Yeah, so this is typically how people have tried and age dated these systems observationally, is you say, oh, we see 24 micron emission, and yet we are able to resolve individual stars. And then there's kind of this 2-point correlation function saying, okay, well, we know the age of the stars. I'm going to put no in quotation marks because there's large uncertainties that nobody actually likes to talk about. Right, so we know the age of the stars, and we see the gas, so therefore the system has to be about this old. Yeah.
All right, let's thank Tobin again.